our seismic noise. When the seismic noise is a lot, then so we basically took a part of data where we consider it to be authentic and we have less noise, and so we define. So I read somewhere that we basically correct me if I'm wrong, that we basically take the time interval to be 30 minutes. I think, am I correct? Yeah. So we take it to be 30 minutes and then divide time interval of 30 minutes.
One short question. In equation 16, on the right hand side, I wonder where the bracket is supposed to close, like because the the first bracket doesn't close.
This is just the type.
Yeah.
Here it
Yeah.
should be closed.
Okay.
Yeah, so basically what I've done is that I'm showing the relationship between parameters. This vector is basically the phase parameters, and I think I forgot to mention that we can model our strain to be like this. So in this way the relationship is very obvious between parameters. So here I'm using the Einstein summation convention. So these are basically a sum of 4 values, which basically the I runs from 1 to 4. So these are basically, and we have 4 quantities of A1, A2, A3, A4. So yeah, so here I'm modeling it to be as a vector.
Okay.
Just to simplify it.
Okay. Because
so these are basically A1, A2, A3, A4.
Yeah, no, it's just that the straight bar in the context of likelihood estimation also often means that you have prior parameters, like different probabilities.
Yeah.
So that is why it's very
sorry for the confusion.
confusion.
This is a typo here.
Yeah.
This is basically a scalar product, and this is the h depends on the and the phase parameter. Yeah. So one other thing we can observe from this fact is that our strain is basically depending on these amplitudes linearly.
Yeah.
These AI, okay, and what we can do about is that and the other values, other parameters which are basically the phase parameters. Our strain depends on a non-linear way. So there is a problem that we can't maximize analytically over phase parameters, but we can do it for the amplitudes AIs. We can simply, because they have a linear relation, we can analytically maximize over them. Yeah, so then we define the data analysis technique, and let's see. Yeah, so if we substitute our model signal here, then what we get is this kind of form where our log likelihood function is this, and the simple AIs are basically the amplitudes, and XI and MIZ are defined like this. So this is basically, these are basically the scalar products of signal with signal and the data with signal. XIs are the scalar product with signal and the data. So as I said earlier that the amplitudes have a linear relationship with, so we can analytically maximize over them, and if we maximize over them, then we get this form of AIs, and if we substitute back into after maximizing it, we're getting this form of AIs. This is a maximized version, and if we substitute back this into our equation 19, we basically get the maximized version of log likelihood maximized over amplitudes AI. So this is basically this is what we called as the F statistic. This is the F statistic. I think everyone was anticipating what F. So yeah. So one thing I think my I am not in the practical field of data analysis yet. So but yeah, so I've done the theoretical part only. So my understanding is that in principle we can through parameter estimation technique we can maximize this form of log likelihood function as well. But I think there are a lot of parameters. I think this is why we are reducing it into two separate problems, which we are going to discuss. First, we basically maximize over amplitudes. Then after this, we basically I'll show you that later. Yeah, but I think correct me if I'm wrong, that in principle we can use this form as well. In that case, even because the parameters are there are 8 parameters.
But you can't find a closed form for the maximization over the other 4 as well. So the beauty of the amplitude parameters is that you can do it analytically.
Yes.
Okay.
Yes, we can simplify it, but in principle.
And you've derived it. That's the closed form analytical maximization.
Yes. But in principle, we can do it.
Well, we can compute the likelihood, basically the log likelihood. We actually need the data to compute it. We can't just do it. It depends on the data. So we have to compute it, and then we have to look where's the maximum where is a high value.
Yeah, so the maximized version of log likelihood function is called the F statistic, and the x2, x4, x1, these are basically the xi's are defined earlier. This is basically a scalar product of the signal with the data. Moving on to the next slide. So one thing I wanted to mention is that we have our F statistic. Okay, we have our so one thing if we measure we have a data and we measure a specific value for F statistic, let's say 30. So what does it mean for F statistic to have a value 30? Is it good? Is it bad? What can we say about our signal based on that value? So and one more thing, looking at this form, F statistic is basically statistical. The name also shows that it is basically a random variable, basically a multivariate random variable. So what we are going to do is basically estimate estimate the probability distribution of F statistic to basically gain insight into we have our result, then how can we analyze it. So after we have to find the distribution of F statistic to say something about the detection, whether there is a detection, where there was a false alarm, something where we have so we have to find the probability distribution. So looking at the basically our F statistics is basically depends on the xi's, and xi's are basically are defined like this. This from equation 20, that xi's are basically depends on the data and the signal. But we initially considered that there are two hypotheses. Our data might contain a signal or only noise. But a signal plus noise. So our data is basically probabilistic in nature, and we consider the noise to be Gaussian in our case, because in reality noise is not Gaussian, but we, as I said, we only take a smaller portion of the data. So for a small interval of time, we can approximate it to be Gaussian, zero mean unit variance noise. So if we have if we model our signal, then there are basically two cases when there is noise and when there is signal plus noise. So we have to find probability distribution accordingly to determine, basically what we are aiming is to determine the false alarm probability and detection probability. Yeah, so first we have to, as I said, basically the f statistic is basically depends on, the xi's, and xi's are basically depends on Gaussian, so they have a linear relationship, so xi's must be Gaussian also, or they must have a normal distribution as well. So what we do is then we basically find that the xi, in the case of when there is a signal, we basically find its mean and its covariance matrix, because basically we consider it to be x1, x2, x3 as a vector multivariate Gaussian vector. Yeah. So, but when we find our covariance matrix, we see that it is the non-diagonal elements are non-zero. But does it mean is that basically the